This is just going to be a quick mini lesson, if you will, on how complex numbers work. So if we were in a live setting, I would have you turn and talk about these two questions, but let's just discuss them here in our video. So what is the distance between x equals 4 and x equals -2? So if we were to think about those on a number line, here's 0. So one of our points is at -2. One of our points is at 4. And so the distance between those two, we could think of that as 4 minus -2, which is 6. You could count that those are 6 units away from each other. Any of those methods would be just fine. We then want to look at the distance between 2 points in a coordinate plane. And so if we look at the point -2, 3, and 4, -5. Now we want to figure out what the distance between these 2 points are. And instead of trying to figure that out kind of on the diagonal, the way that we're going to do that is with Pythagorean theorem. So if you make a right triangle, the change in the height of this triangle is 8. The change in the width of this triangle is 6. If you know your Pythagorean triples, 6 is 3 times 2, 8 is 4 times 2, so the hypotenuse must be 5 times 2, so the hypotenuse must be 10. If you needed to do 6 squared plus 8 squared equals c squared, we get 36 plus 64, we get 100 equals c squared, and so you end up getting 10. You could also use the distance formula, okay? And so the distance formula says, hey, take the change in your x's, so 4 minus -2, and square that. Add to that the change in the y's, -5 minus 3, and square that. I get 6 squared plus -8 squared, square root. That ends up giving me the exact same formula as the Pythagorean theorem if we use distance formula. All right, let's talk about this now in the complex number system and where we're going with this. So how we graph in the complex number system is we use the x-axis or the horizontal axis to be the real number. And then we use the imaginary axis as the y. And so for all complex numbers, a plus or minus bi, we then are going to use the coordinate plane to graph this. Again, where a gets graphed on our x-axis and b gets graphed on our y-axis. And then we can figure out the distance between 2 points, and we can do that the same way we would find the distance between 2 points in any rectangular plane, okay? So if I just had a number like 3 plus 4i, and if I wanted to know like how far away is that from the origin, like what is that distance from the origin, then I could make this a 3, 4, 5 triangle. And you can see our notation kind of in this other example here. If this is z equals x plus iy, then the length of z is one way we say that would be 5. If I needed to figure out the length between 2 coordinate points, here's an example if you want to look through that. I want to kind of get into where we're going with this. So if you want to pause and look at that one, you can. All right, so Euler, not Euler, but Euler came up with his own formula in complex analysis that talks about both trig functions and exponential functions and how they kind of coexist together. So Euler's formula says that for any real number x, we can represent e to the ix as this trig sum. And let's just talk quickly about how that kind of comes to be. Think about the unit circle. Okay, so if you notice, this is the real number 1. Anywhere along this circle here, if you were to take a vector from 0 that's on the circle and drop that perpendicular to the real axis, we know from pre-cal that the x component is cosine and the y component is sine. Now, if you think about that in terms of how we were to graph this point right here, remember we called that like x plus iy. And so Euler's formula says that that point can be written as e to the I phi is technically what that angle is instead of theta. It's a phi, okay? So let's kind of talk about this a little bit. Sorry, there's a typo here. E is the natural log base, I is imaginary unit, and sine and cosine are just normal trig functions. Now, if you looked at e to the negative I, then it just so happens that you'd end up, and I believe there's supposed to be an x here, okay? You'd end up having just the opposite sign. Sine and cosine are even and odd functions, and so you end up just having like the conjugate, if you will, over here. There's a lot of algebra that then goes into play as to how we can add and subtract these. You are not going to have to know for our class why that's the case, but if you are interested, here is why. I think when I translated the Word file over to the PDF, it's missing a couple things. Like it's missing the X right here. It's missing a beta right here. I'm not sure why it did that, but that's what happened. Okay, sorry about that. So since this must be true for any set, if you do this linear combination, you do some figuring out here. This is where we are going to end up getting our solution. Okay, and there's a beta. I don't know why it didn't transfer over, but there's a beta right there, okay? We know based on this class that if I have two solutions for a second order differential equation, C1 and C2 must be true for anything in the general solution. So we'll get to that in just a second, but this is where we're going to go when we have complex solutions. Okay, in our auxiliary equation, I have a hard time saying that word, auxiliary equation. And so it's important to understand when we get to those complex solutions, like where this next piece kind of goes, okay? So since C1 and C2 could be anything, we could kind of create a system of equations here. Again, more algebra, more trig, some really important like trig identities are involved and all of that. And essentially what ends up happening at the end of all of this is if you end up having a solution curve or any set of complex conjugate solutions to what we're going to call the auxiliary equation, you can rewrite this as this trig and exponential function combination. So looking at these practice questions, if you kind of map this out, this is saying that alpha equals 2 and beta equals 3. So if I wanted to rewrite this in terms of sines and cosines with the e function so that I no longer have imaginary things in my exponents, because like that's really weird and crazy, then I can write this as C1 e to the 2x cosine of 3x plus C2 e to the 2x sine of 3x. All right, let's look at this one right here. Here I have two different pieces. So let's look at this conjugate pair first. I just have an IX. So in that case, and it's a plus or minus, what that means is that alpha must be 0, okay? Because I must have a 0 in the front of that plus or minus piece. And beta must just be 1. Okay, so I would have for this first part, C1 e to the 0x cosine x plus C2 e to the 0x sine x. You can think about this together as a pair is C e to the plus or minus ix, and it's just kind of separated out, okay, using the terms of exponents that we can do. And then that exponential function, if you were to map it in the coordinate plane, corresponds to a sine and cosine of this function, okay? Over here, I have an x in the front. And so notice I'm going to keep that x, but my alpha is still 0 and my beta is still 1. So I have C3 x e to the 0x cosine x plus C4 x e to the 0x sine of x. Now e to the 0 is just 1. So this whole solution right here ends up becoming, I'm just going to write it up here, C1 cosine x plus C2 sine x plus C3x cosine x plus C4x sine x.